Our final speaker, Josh Izaac, is a theoretical physicist who received his PhD in quantum and computational physics at the University of Western Australia. He's the quantum software team lead at Xanadu, and I must say, he is an excellent baker. Josh, I miss your Raspberry Pi. I understand you've also been working on your sourdough over the last year or so. So all is going to be forgiven as long as I have access to that first batch when you're back in Toronto. So, Josh is actually not in Toronto right now. He's joining us from Western Australia. He's stayed up way past his bedtime to give us a hands-on demo of quantum differentiable programming with PennyLane. So with that, please take it away, Josh.
Hey everyone, my name is Josh Izaac, and today we'll be going through a guided walkthrough of PennyLane. So I'm a quantum software developer here at Xanadu, and one of the lead developers of PennyLane, a Python framework for quantum differentiable programming. I'm super excited to show off how you can do quantum machine learning with PennyLane. So let's get started. First of all, let's go through a quick overview of what we'll be exploring today. So we'll start off with the basics. How to construct quantum circuits in PennyLane and evaluate them by dispatching them to various quantum simulators and hardware. Next, we'll explore integrating your workflow with machine learning, how we can differentiate quantum circuits, train them, and optimize quantum algorithms in PennyLane. We'll go into more details about how we can find gradients of quantum circuits and train hybrid models. Finally, we'll briefly explore the various plugins and devices we have available in PennyLane. PennyLane comes available with a huge variety of performance simulators for rapid prototyping, but we also provide a range of plugins, allowing PennyLane to make use of external simulators and hardware devices. This includes photonic hardware, trapped ion hardware, and superconducting qubit hardware. You can even construct models that include multiple quantum devices in a single calculation. Before we get started, I just want to show off two very useful resources that will complement the tutorial session today. So the first one is the PennyLane documentation, which I just have open here. You can find it by going to pennylane.ai and just clicking the documentation link in the nav bar at the top. So this is the place to go to find out about every functional object in PennyLane. They're all listed down here in the API section in the table of contents. But a really useful reference section is the top left-hand side, using PennyLane. Think of them as reference guides to the core parts of PennyLane. I know going through a new software package from scratch can be a bit overwhelming, so at any point feel free to stop and have a look at any of these reference pages. These detail tips and tricks for circuit construction, available quantum operations and measurements, and various other core components of PennyLane, for instance, creating devices. A second really useful resource is the PennyLane QML website. This page contains a huge array of PennyLane demonstrations and tutorials, from short introductions such as qubit rotation and using plugins in different devices, to introductions to various qubit algorithms such as VQE and QAOA. And finally, it contains implementations of the latest results from the quantum machine literature. So, let's get started. For this tutorial session, I'll be working directly in the terminal. Feel free to follow along or simply watch and learn. Let's get started. So today I'll be coding live from my Python terminal. Feel free to follow along as well using a Python terminal if you so choose, or Jupyter Notebook or even Google Colab. All the commands I use today will work in those three environments. So this is a completely clean environment. I'm going to start by installing PennyLane, and that's super easy. Simply pip install PennyLane and it will be downloaded from the Python repositories and installed. I'm now going to drop into an IPython session and we can get started playing around with PennyLane and building our first quantum circuits. So we always start off by importing PennyLane as QML, and this is the convention we use across all of our demos and documentation. So every time you see something starting as QML dot, that's a function or an object we're using from within PennyLane. Now that PennyLane is installed, we can build our variational quantum circuit. So let's create one here. Now in PennyLane, variational quantum circuits are always Python functions. functions. So here I'm creating my QFunc, or quantum function for short. It takes two arguments, x and y, and these are the input gate parameters to our variational quantum circuit. And I'll start by having a Rx rotation, taking parameter x and y0, and a Ry rotation that rotates by value y, also around y0. So a very simple circuit. And in PennyLane, we use the terminology y's to refer to qubits. So by saying y is equal 0, I'm applying Rx rotation to qubit 0 and Ry rotation to qubit 0 in this circuit. And a variational quantum circuit must always return a measurement statistic. So that's what I'll do here. I'll return the expectation value, so QML.xval, and I also always need to specify the observable that I want the expectation value of. So I'll measure the observable Pauli Z, also on y0. And measuring the expectation value of Pauli Z on y0 is similar to measuring in the computational basis. Perfect. So let's now evaluate our quantum function. So this might not be what you expect. We evaluated the quantum function and we just got back an unevaluated measurement statistic, our expectation value of Pauli Z and y0. If we want to actually evaluate this quantum function and get numeric output, we need to bind this quantum function to a quantum device. So that's easy. In PennyLane, we can create a device using QML.device and specify the device we want to load. In this case, I'll just load default qubit, which is our built-in qubit simulator for rapid prototyping. And I'll say that I want to provision this device with 2 Ys. So now that I've created my device, I can take my quantum function, and this time, instead of defining it as I did before, I'm going to decorate it with the QNode decorator. And what the QNode decorator does is it takes our quantum function, our variational quantum circuit, that applies quantum operations and returns a measurement statistic, and it binds it to this device. So now, if I evaluate it, you'll see that I get a numeric value, 0.9751. So this is the expectation value of the Pauli Z observable on y0 after I've applied an Rx rotation and a Ry rotation to that qubit. So if I just print this, you can see that this is now a QNode object. And what we can actually do is we can apply various other functions in PennyLane to manipulate and transform this QNode. So one function we have is a draw function. And what this does is this takes our QNode and turns it into a function that prints out the variational quantum circuit. So let me print this, and I'm passing in the parameter value 0.1, 0.2. These are the parameters I want to print the circuit with. So there you go. That's a variational quantum circuit. We're applying an X rotation of 0.1, then a Y rotation 0.2, and we're measuring the expectation value of Pauli Z. So now let's make something a little bit more complicated. So here's our QNode from earlier. What I'm going to do this time is I'm going to take the Y rotation and now apply it to a second qubit. So now we have a variational circuit running on a device with 2 qubits. And I'll take a C NOT gate and apply this to entangle Y01. So now we've got 2 qubits both being rotated and then being entangled. And now that we have 2 Ys, rather than just returning expectation value on the first wire, we can also return another measurement statistic on the second wire. In this case, I'll return the variance. And just to spice it up a little bit, we'll do the variance of the Pauli X observable on Y1. And we can evaluate this. So now you see our output has 2 values. This first value corresponds to the first measurement statistic, Pauli Z expectation value, and this is the variance of Pauli X on Y1. This is Pauli Z, sorry. Perfect. And PennyLane has lots of built-in operations, lots of built-in measurements. So all the gates you know from the qubit model are available in PennyLane. For instance, the Hadamard gate. We also have Pauli Z, Pauli X, the U3 gate, the rotation gate. But let's go through a couple of different measurements we have in PennyLane. So here's the same variational circuit from above, the same QNode from above. This time, I'm going to ask for the probabilities across both Ys. So this will give the full probability of the system. And probabilities are in essence a measurement statistic, so this is something that will produce deterministic output. So executing this, there you go. We now have an array of 4 values. This corresponds to the probability of measuring the circuit in state 0, 0, 0, 1, 1, 0, and 1, 1. And you can see just by quickly glancing over it that the probability of it being in the 0, 0 state has the highest probability. We can even request marginal probabilities. So let's just ask for the probability on y1 on y0, as well as the marginal probability of y is 1. So a slightly different output now, the 2 by 2 matrix. The first row corresponds to the marginal probability of y0, so this is measuring the first wire in the ground state and the excited state, and likewise for the second wire, ground state, excited state. Awesome. And if you're using particular devices, so in this case we're using default qubit, which is a state vector simulator. So under the hood, the state is actually being simulated. It supports an additional measurement statistic, a measurement property that isn't supported on other devices that aren't state vector simulators, which is the ability to return state. So this actually allows you to extract the complex state vector at the end of the variational circuit evolution. So everything we've been doing here, we've been doing on the default qubit simulator, and we've been doing exactly. So it's been evolving the state vector underneath the hood, and then once the state vector has been evolved, it's been computing the exact expectation values. However, we can modify this, and we can have this default qubit simulator working as a sampling device. And this is relatively easy. So for instance, I'll create a new device now, still default qubit, still over 2 wires, but this time I'm specifying analytic equals false and shots equals 100. So we're not using this device as an exact simulator, an exact state vector simulator. We're using it in sampling mode by specifying analytic equals false. And we're asking for all measurement statistics to use 100 shots or 100 samples under the hood. So I'll go back to our original Q node, very simple one, Rx and Ry over a single wire. And I'm binding it to this new device that samples rather than calculates exact expectations. So now if we execute it, we see that every time we execute it, we get a slightly different result. And this is because every time we execute it, 100 samples are being generated, and these 100 samples are being have a statistics applied to them, in this case, expectation value or a mean, and that's how we're retrieving the result. You can see that it varies quite a lot. So let's create a new device, but this time with a larger number of shots. So 1,000 shots. So this will be generating 1,000 samples under the hood. So here's our Q node bound to this new device, and let's execute it a couple of times. There you go. So you can see it's still a bit stochastic. Every time we execute it, we get slightly different results. Because we're using a larger number of shots, the variance in our results is significantly reduced. And so when you're using PennyLane with hardware devices, you'll be always using a sampling device. So you'll need to specify the number of shots you want to use in order to compute the measurement statistics of your Q node or variational circuit. So now that we've explored how to build a variational quantum circuit using Q nodes in PennyLane, let's do something a bit more complicated. Let's create a variational quantum circuit and find the quantum gradient of it. So I'm going to start off by creating a device, and like before, I'm going to use the built-in default qubit device and ask for 2 wires. So now I can create my Q node. So I'm binding it to this device and creating my circuit quantum function. So in this time, I'm just using a single argument as the parameter. This will be an array or a list. And I can index into this for the particular parameters for the gates. So X rotation, using the first element of the parameters on the first qubit, or Y rotation using the second parameter on the second qubit, second wire, and then I'll entangle them, I suppose. Now maybe I'll do a RZ rotation. So rotation around the z-axis using the next parameter, this time back on the 0th wire. And just to mix things up again, maybe I'll repeat that parameter. So I'll reuse that same parameter but in a different gate, but on a different wire this time. Do a bit more entangling. Actually, maybe this time we'll entangle it backwards. So have the control wire y1 and the target wire y0. And just for fun, we'll add a header mod on the first wire. And we can now return our expectation value. And this time I think I'm going to ask for a tensor product. So we'll do tensor product of Pauli z and y0 with Pauli x and y1. And here the at symbol is just shorthand in PennyLane for doing the tensor product between two different observables. And I want the expectation value of this tensor product observable. So before we go any further, I need to import NumPy. So this might look a bit odd if you're not familiar with PennyLane, but rather than just importing NumPy, normally I'm going to say from PennyLane, import NumPy as NP. And the reason I'm doing this is because PennyLane ships with a special wrapped version of NumPy provided by the AutoGrad library. And what the special wrapped version of NumPy does is it enables automatic differentiation. So this version of NumPy will keep track of the gradients as you apply operations, and then allow you to backpropagate through it using the same NumPy API that you might already be familiar with. So let's create our parameter array. Params NP array, let's say 0.1, 0.2, 0.3. And we can specify that requires grad equals true. Or in other words, we want this array to be marked as a differentiable array so that the gradient is tracked throughout the entire process. So let's evaluate the circuit. So that's our expectation value, 0.189. So how do we compute the gradient? Well, it's relatively easy using the PennyLane NumPy provided backend. We'll create our grad function first. So we have a function qml.grad, and we apply it to our quantum node, our key-node circuit. And this is just another function. So what we can now do is we created a function that evaluates the gradient of our variational circuit. We can call this at various different parameters, and this will give us the gradient at these parameters. So at these parameters, 0.1, 0.2, 0.3, the first parameter has a gradient essentially of 0, 10 to the minus 17. But you can see that the second parameter and the third parameter both have non-zero gradients. So let's verify this quickly manually using the parameter shift rule. And the parameter shift rule is a way of using quantum hardware or existing quantum devices to evaluate the gradient of the quantum device. And there's more information about the parameter shift rule on the pennylane.ai/QML website if you're interested. So essentially what we're doing here is I'm creating a shift array. And what the shift array does is it provides no shift to gradient to parameter 0. That parameter 2 has a shift of pi on 2. And then parameter 3 has no shift. And this allows me to construct the parameter shift rule to verify the gradient. So what I'm going to do is I'm going to evaluate the circuit on our params, but shift it forward in the second parameter by pi on 2, and then subtract another circuit evaluation, but this time with that second parameter shifted backwards. And then I divide the whole thing by 2. And you can see that this parameter shift rule done by hand provides the gradient of the second parameter that agrees exactly with the result that we got previously when we had PennyLane compute the gradient of our Q node. And you might be wondering how PennyLane calculated the gradient of our Q node before. So if we have a look at the Q node decorator and we just bring up the help, we go down, there's a keyword argument called diff method. And diff method takes various strings as arguments. By default, if you don't provide anything, the differentiation method will be best. So PennyLane will try and work out what's the best differentiation method to use for the device and the circuit you've provided it. And the nice thing is that PennyLane provides various different ways of specifying if you want an exact differentiation method. You don't want PennyLane trying to determine the best approach. So you can use backpropagation. So this is just standard classical backpropagation. If you have a simulated device that itself is end-to-end differentiable, PennyLane can just backpropagate through the simulated device. And this is what was happening with default qubit. Default qubit supports backpropagation, so PennyLane was choosing backpropagation as the best approach, the best method for computing gradients just now. The next two approaches, reversible and adjoint, these also only work on simulators. But what these do is these provide a modified backpropagation algorithm. And this modified backpropagation algorithm takes into account the fact that quantum computation is unitary. And because it's unitary, we can take advantage of various efficiencies with backpropagation. So for example, it has lower memory usage or lower compute time than standard backpropagation. Finally, you can see that PennyLane has some hardware-compatible gradient methods: device, parameter shift, and finite diff. The nice thing about these three methods is they all work on hardware. So if you're using a hardware device like IBM Q or Amazon Bracket, you can specify parameter shift as your differentiation method, or if you're using BEST, PennyLane will automatically deduce it needs to use parameter shift, and quantum gradients will still work even on hardware. So I can go back up to our definition of the Q node earlier and test this out. So in the Q node decorator, I'm going to say diff method equals parameter shift. And this will force PennyLane to use the parameter shift even though we're using the parameter shift rule for quantum gradients, even though we're using a simulated device. So I'm now redefining our gradient function with this new Q node circuit. And as before, I can just evaluate it. And there we go. It's now computing the gradient using the parameter shift rule. So in this case, we've calculated the gradient of a Q node or a variational circuit directly, but PennyLane also works with hybrid classical quantum cost functions. Let's create one now. This cost function takes our quantum parameters. It also takes an additional parameter y. And the first thing we're going to do with this quantum function is we're going to evaluate the circuit. But we'll add in a little bit of classical processing, because why not? So first we'll take the sign of the parameters, and then we'll add y. And these will be the parameters that are fed to our variational quantum circuit. So we've had a little bit of classical processing before evaluating the circuit. We evaluate the circuit. Now we can do a bit more classical processing. So for instance, let's take the cosine of the output of the quantum circuit, and we'll take the cube as well. So there you go. That's the value of our cost function evaluated with the same parameters and y equals 0.5. And just as we did above, we can generate, small change here, rather than generating the gradient function of the circuit, we want the gradient function of our cost function. And this gradient function always takes the same parameters as your cost function. So the cost function takes parameters, 0.5, and there we go. That's the gradient. So we've got a tuple of two arrays. The first one is the gradient of our parameters, and the second one is the gradient of the second parameter, 0.5. So that's how we can use hybrid classical quantum cost functions in PennyLane, both for evaluation and gradients. So feel free to play around. The cost function I've got here is quite simple, but you can almost go wild. You can have a cost function that uses multiple quantum nodes, multiple variational circuits, and have the output of one feed into the input of the other. Do even more classical processing. And PennyLane will still be able to calculate the gradient, both on simulators and on hardware. So now that we've explored how you can use PennyLane to calculate quantum gradients, we can start to take advantage of one of the workhorse algorithms of machine learning, which is gradient descent optimization. So in my terminal here, I've imported PennyLane. I've imported the auto-differentiation compatible version of NumPy provided by PennyLane and AutoGrad. And I'm creating a quantum device. Again, I'm just using default qubit. I'm instantiating it with one wire. So you can see here I've got a very basic Q node. This Q node is only a one-wire Q node. It's bound to the default qubit device. It has an Rx rotation on Y0, and then another parameterized Ry rotation on Y0. And then finally we output the probabilities. So I've created a set of initial parameters, 0.1, 0.2, that we can feed into our. There you go. So what's actually happening here? So we're outputting the probabilities on y is 0. The first element is the probability of measuring the variational circuit in the ground state. And the second element is the probability of measuring it in the excited state. So you can see that with the parameters we just chose, our initial parameters, probability of measuring in the ground state is quite high, and the probability of measuring in the excited state is relatively low, about 1%. So what we can do here is we can turn this into an optimization problem. Can we optimize the parameters of this variational circuit so that we can maximize the probability of measuring in the excited state while minimizing the probability of measuring in the ground state? Let's give this a go. So the first thing we want to do is we want to create our cost function. And what the cost function encodes is it encodes the value of our optimization problem that we want to minimize. So I've defined my cost function and takes input parameters. And the first thing I want to do is I want to evaluate the Q node we just created and get those probabilities extracted from the system at these parameter values. So now that I've evaluated the Q-func, I have output, which is this probability vector, probability of the ground state and probability of the excited state. So I want to minimize this value. I want to minimize the probability of finding it in the ground state. I want to maximize the probability of finding it in the excited state. So I'll subtract the second element. So this encodes our cost function, and I will return this here. So we want to minimize this value while maximizing this element, hence the negative sign. Let's test evaluating this. So the value of our cost function is actually quite high, 0.97. And this indicates that we're probably quite far away from the minimum, as we know. We can see that we're not at the minimum of our cost function, because the minimum of our cost function will have maximized this excited state probability. So what we can do now is we can use gradient descent to iteratively update the parameters to minimize this cost function. And PennyLane provides a suite of built-in gradient descent-based optimizers. I'll just create one here. This is a basic gradient descent optimizer with a learning rate of 0.1. So now that I've created the optimizer, I can create the update loop. So this is just a simple for loop for I in range 50, and this for loop will be called for 50 steps. And what I want to do in each step of this for loop is I want to update the parameters based on this gradient descent algorithm. This is relatively easy in PennyLane. I've already defined my optimizer, so I can just call op.step, and I pass to it the cost function I want to minimize and the parameters. And what it will do is it will evaluate the gradient of the cost function and determine how we update the parameters to minimize this cost function. And we're storing them again in the same variable params. However, there's another method that I might use here that's not op.step. It's op.step in cost. And the nice thing about this is it doesn't just output the new parameters, it also outdates the cost value. So it saves us having to evaluate our quantum function again, especially if we're using a device where we have to be wary of the number of quantum evaluations we're making. So now I'm outputting the parameters, the updated parameters, and the cost function value at those parameters. And just so we can keep track of how our optimization is going, let's print out each step number and the cost. Awesome. So let's run this for loop. Brilliant. So if we scroll back up to the top, you can see that at the first step, the cost was still relatively high, 0.97. And as the gradient descent optimization proceeded, this cost function was gradually minimized until we hit a minimum of 0.97. And these are the output parameters. So recall we started with parameters 0.1, 0.2. And after applying 50 gradient descent steps, we found a minimum of our cost function with these parameter values. However, the cost function value doesn't really tell us much. Have we minimized the probability of measuring the ground state and maximized the excited state? So to do this, we can actually evaluate our Q node with these new optimized parameter values. And you can see we've done a pretty good job. So the ground state now only has a 1% probability of being measured, whereas the excited state is almost 99% probability of being measured. And if you want to play around with this, you can even increase the number of steps, and you should see that you should be able to get a minimum cost function value of -1 and get an even higher probability of measuring the excited state. So I've shown you the gradient descent optimizer, but I just want to quickly go to the quick start in the PennyLane documentation. And if you're using the built-in NumPy backend of PennyLane, we provide a whole suite of optimizers. And these range from standard ones like atom optimization to ones that are quantum specific, like the QNG optimizer or the rotosorval optimizer. And these optimizers, they take into advantage the specific quantum geometry of the system and provide even faster convergence in certain cases. And I won't go into them here, but I can recommend you check out our QML tab and go to our demonstrations. We have a whole section on optimization, and these cover some of these new results in quantum optimization. The cool one is the accelerating VQEs with quantum natural gradient descent. If you're interested in problems like VQE, what this demonstration does, and I'm just going to scroll quickly to the bottom, is it shows that by choosing this quantum aware optimizer, the QNG, it converges significantly faster compared to standard gradient descent optimizer like we just did. And you can see that in the optimization landscape, the quantum natural gradient descent took a more direct path to find the minima. So do check out our documentation and our tutorials and learn more about all these different quantum optimization techniques. So far, when creating QNodes, we've simply been using the built-in default qubit simulator. However, PennyLane is actually framework and hardware agnostic. We can create QNodes and quantum functions and bind them to different simulators and hardware devices, and even create a single model or cost function that has multiple hardware devices in it. So let's have a play around with this now. So in my web browser, I'm just on the PennyLane website on the plugins tab. And this is an overview of all the plugins and devices available in PennyLane. So we have some built-in devices, including default qubit, which we're all very familiar with now, as well as default Gaussian, another built-in photonic simulator. So these all come with PennyLane. Scroll down, however, and we have a suite of plugins, and you can install these plugins separately, and they add support for additional devices to PennyLane. So for instance, the Qiskit plugin allows you to use IBM Q with PennyLane, submit QNodes to be evaluated on hardware on IBM. Alternatively, you can use Strawberry Fields to submit photonic QNodes to be evaluated on Xanadu hardware, the Circ plugin to submit via Circ, etc. So for this session, let's have a look at the Amazon Bracket plugin. So the Amazon Bracket plugin, that allows you to use the Amazon Bracket service to evaluate and optimize quantum models in PennyLane. So this plugin provides two devices, bracket.aws.qubit, which allows you to run circuits on the remote Amazon Bracket service. So you can create your device, specify the endpoint, and then when you bind it to a QNode, this QNode will be evaluated on this remote simulator or this remote hardware device. It also provides a local bracket device, so it just uses the local bracket simulator. And this is the one we'll be playing around with today. But feel free, any of the examples in this tutorial session, when you play around with them, feel free to change out the device. You play around with different devices and explore different hardware with PennyLane. So I'll just go over to my terminal now. And since this is an external plugin, the first thing we need to do is install the Amazon Bracket PennyLane plugin. So this is all the plugins are available on pip. Here we just pip install Amazon Bracket PennyLane plugin. And for any of the plugins, simply refer to the documentation on how to install them. Now that it's installed, I'll go back into IPython. Great. So let's set up a optimization problem that uses multiple quantum nodes running on different devices. So as before, import PennyLane and import the NumPy wrapped version of PennyLane. And now that we've installed the Amazon Bracket PennyLane plugin, we can create our bracket device. And while you could use the remote Bracket AWS device just for this demo, I'm going to use the bracket local device, but feel free to swap it out. So my device is created, and now I can create the Q node. So I'm binding it to the device I just created, device bracket. And I'll just build a very simple Q node here. So the bracket device I created has two wires, so I'll add a RX and an RY rotation, entangle them with a C NOT gate, and just add a how demand for good measure. And finally, I'll output the expectation value of the poly Y observable. So we've created one Q node now that runs on the bracket device. Let's create another one. This time we'll run it on a different device, but let's not even choose a qubit device. Let's go out there a bit. Let's create a photonic device. So I mentioned earlier we have a built-in photonic simulator in PennyLane called default Gaussian. I'll provision that, this time using two wires. And now I'll create this Q node that uses this photonic device. So here it is here. One thing you'll notice straight away is that the photonic Q node uses different operations to the qubit Q node. This is because it's a slightly different model of quantum computation. It uses operations such as squeezing and beam splitters, and even the measurements are different. Here I'm asking for the expectation value of the number operator. If you're interested in these photonic operations and devices, feel free to have a look on the PennyLane website. It goes into detail about all the devices that are supported across qubit and photonic, all the operations supported on qubit and photonic devices. So I've created my photonic Q node there. And just for fun, let's evaluate it, make sure it's giving a nice result. Excellent. So I'm calling the circuit photonic Q node with X value 0.2, Y value 0.6. So I'm squeezing with 0.2 magnitude. I'm using an angle of 0.6 in the beam splitter, and I'm measuring the mean photon number. In this case, 0.027. So I've got two Q nodes now. I've got this circuit qubit that runs on Amazon bracket local simulator. I've got this photonic Q node that runs on the built-in default Gaussian simulator. So let's create a cost function that really entangles the evaluation of these two circuits. So dev cost params. So I think the first thing we'll do is we'll evaluate the qubit Q node. Now let's do something a bit more. Let's take the exponential of it, because why not? So we're taking the exponential of it. Now we might as well evaluate the photonic Q node. And the photonic Q node, remember, takes two arguments, x and y. So the first argument, let's actually pass in the output of the qubit Q node. And the second one, we'll pass it in again, but this time we'll qubit. And finally, we want our cost function to always return a scalar value. So we'll take the sum of the output from the photonic circuit, and we'll subtract the output from the qubit Q node. There we go. So this is definitely a more complicated cost function than we saw previously. We're using two Q nodes on two different devices, and they're not evaluated independently. The evaluation is very dependent on both of the Q nodes. So we can create some parameters just to test evaluating this cost function. So 0.2, 0.1, 0.3. And there we go. So we've evaluated our cost function. And in the process of doing this, we've called both an external bracket device and an internal photonic simulator. How cool is that? Even cooler, it's not just evaluation. As I mentioned before, PennyLane has built-in methods of differentiation of quantum circuits, and it supports differentiation of every external device. So as before, I can call the QML grad function on our cost function. So this generates a gradient function that evaluates the gradient of our cost function. And I want to evaluate it at these parameter values. And there we go. So we have a cost function that entangles two Q nodes, a qubit Q node running on Amazon bracket and a photonic Q node. And not only are we able to evaluate it, but we're able to evaluate the gradient. And since we can get the gradient, we can then use gradient descent and optimize this very complicated cost function. So do feel free to play around, install different plugins, different devices, and try submitting some of these examples to actually run on hardware and optimize them. So thank you for joining me on this whirlwind tour of PennyLane. I hope you've enjoyed it. But I really want to emphasize that we've only just begun to scratch the surface of what PennyLane can do. For example, in all the demos today, we use the built-in NumPy autograd backend of PennyLane. But PennyLane also supports other backends for auto differentiation. So we've been using NumPy autograd, but it also supports PyTorch and TensorFlow and JAX. So you can make use of the built-in optimizers of these frameworks, high-level models such as Keras and Torch.mn, and you can even deploy your classical processing to run on GPUs, while your quantum processing part of the model runs on QPUs. Not only that, but we have built-in quantum chemistry in PennyLane, so the ability to compute molecular Hamiltonians and embed them into Q nodes to run algorithms such as VQE. We have a templates library in PennyLane, and this templates library is a collection of different embedding and layer ansats that can be super, super useful when building up your quantum machine learning model. So before you go, just a reminder to check out our website, go through our documentation, and don't forget to check out the many demos we have online. If you follow us on Twitter, PennyLane AI, we're constantly updating and releasing new demos, so you can see them just as they've gone live. Thank you, everyone.
Fantastic, Josh. That is great. So I really wanted to take some questions from the chat, but Josh is such a good multitasker. He was answering all your questions while simultaneously coding all that up. That was awesome. There was a common question. A lot of people in the chat were wondering why the parameter shift rule has such a large shift of pi by 2. Could you say something about that?
Yeah, so this is actually a big reason of why the parameter shift rule is so useful. So I think when you first look at the parameter shift rule, it's very easy to look at it and think, oh, that looks so similar to finite differences. And when you're doing something like finite differences, you want to take a very, very small shift, something like 10 to the minus 7 or 10 to the minus 6. And typically, the smaller shift you go, the more accurate your results. This is because finite differences is an approximation, and it's only true in the limit for the shift being very small. With the parameter shift rule, however, that's not the case at all. The parameter shift rule is an exact formula for the gradient, so it holds no matter what shift value you have. So then the calculus changes a bit. We want to choose a shift value, because we know any shift value will work, but we want to choose a shift value that's ideal for evaluating gradients on quantum hardware. So in this particular case, we want to maximize the shift in the optimization landscape or the geometry of the quantum function. We want to sample the quantum function from two places in the parameter space that are far enough apart from each other that when we do sample them, we're not swamped by noise on the quantum device. So it's very deliberate that we choose a shift of pi and 2 in that maximizes the distance in the parameter space where we're sampling the gradient from.
Cool. Very informative. So in addition to answering all these questions in the chat, I know you're very prolific in answering people on GitHub as well. Why are you so responsive to this? I mean, you could easily just sit back and develop the software. Why are you so engaged with everybody?
I think that comes with software development. It's something I really love. So my background, I'm a quantum physicist. I did my PhD, and as those from academia, whether undergraduate or postgraduate, know, when you're doing research, the feedback loop between getting feedback based on what you're actually doing right now in your research and what other people in the community think is very, very long. So typically you write a paper, you submit it, it goes through review, you get feedback a couple of months later, you make changes, you submit that again, and that holds for research papers, even holds for something like an undergraduate thesis or a PhD thesis. The really, really cool thing about quantum software and this quantum ecosystem that we currently have is that you can build in these amazing new features from the cutting edge of the literature, and you can get feedback almost immediately. As soon as we make these releases of PennyLane, we have people eager to try it out, and not only try it out, but do things that we didn't expect them to do with it, and even break it. And it's so valuable to be able to get that feedback so instantaneously. And it's really driven how we develop PennyLane. So it's super, super important for us. Examples being, we would sometimes release features thinking, okay, it has to be done like this. And straight away, we see that people are trying to use it in a completely different way that we didn't expect. And it's really tempting to say, no, stop, don't do it, you're doing it wrong. But when you stop and you think about it and you interact with everyone who has this amazing feedback, you realize that, hang on, we could take into account this feedback and make it better. But to be able to do that, you have to interact, you have to chat to people who are using the software and find out how they're using the software and how you can improve it to make it better for their workflows. So yeah, it's something I really love about quantum software, the fact that we can interact so easily. And the boundary between being a software developer working on quantum software and being a user on quantum software is very free. You can go from playing around with quantum software to being able to very easily develop for it just because it's open source and available on GitHub.
Right. Yeah, and anyone could contribute, right? I mean, open a PR on the PennyLane repo, and there you go. That's super cool.
Exactly.
So, I mean, with so much development behind you with PennyLane, I mean, with the 14 major releases now, you're kind of locked in, I guess, to a path to a degree. Is there anything that you would change if you could do it all over again and start from scratch? I know.
So it's something I think about a lot. And there are times where I wish I could take a week off from work, so tell everyone I'm taking vacation, but then actually to create a pseudonym account on GitHub and fork PennyLane and rewrite the bits I want to rewrite. But yeah, there's actually so much that I would like to change, because you always start off a software project having a grand idea of what you want to do, but it's very hard to see the full picture right from the beginning. You don't even know how people want to use your software. So all this information we've learned over the last 4 years from our great team of internal developers, plus all the contributions we've gotten and just talking to people and asking how they want to use quantum software, that's definitely changed our thinking along the ways. And yeah, so
Okay.
to answer your question, there are tons I would love to rewrite.
I'd love to hear what are some of the surprises of what people want to do with PennyLane that kind of didn't occur to you.
So in the beginning, PennyLane wasn't as flexible as it was now. When you wrote a Q node, it had to be quantum inside of it, and it had to be classical outside of it. And we tried to say this in the documentation. We would say things like, don't put any classical processing inside your Q node. Don't do addition, don't do multiplication, just have quantum operations. But very quickly, we noticed that sometimes you want to put classical processing inside the Q node. Sometimes you have no choice. You have a decomposition that requires classical computation, and you want to do this in a way that's differentiable. So this was a really, really big thing for us, and talking to people, and even internally, this was something that we wanted. So this was actually a huge change that we implemented across version 0.13 and 0.14 of PennyLane to make it so that you can now put classical processing inside QNode, and that remains differentiable. And this is actually, it sounds trivial, but it's really, really cool once you dig into what it's capable of, because you can now have compilation of quantum operations happening inside your quantum function. And that decomposition or that compilation itself is differentiable, and you can train that. So that's a huge feature change that came about just from chatting to users and seeing what they wanted.
That is really cool. I'm looking forward to seeing what people come up with that for sure. Speaking of documentation, I know I read a lot of software documentation myself. I think I'm maybe a little bit biased, but I think PennyLane and Strawberry Fields documentation is quite good. Do you guys have do you outsource this to other people, or how how are you able to do that?
I think sometimes when we talk to other people, they're surprised at how much of the documentation the core development team themselves write. So the core development team is not only just writing the API documentation, but we're also writing the quick starts and we're writing the demonstrations and the tutorials. It's something that we really highly prioritize. We we want to take a documentation first approach, because if you can't read the documentation of software product, then you won't be able to use the software product. So we always have internally a very, very high goal and a high standard when it comes to our documentation. And just writing these tutorials where we implement the latest from the QML literature, it helps us even in terms of our development. We can see, oh, I can't do this in PennyLane. Why haven't I implemented this functionality? And then you go back and you take that into account when you make changes to the source code.
Yeah, it definitely shows, and I think that's a fantastic approach to have the developers, yeah, really writing that documentation, because yeah, I think it's a massive value add to the software for sure. Maybe let's shop talk now, since we're getting close to the end of the session. I want to hear a little bit more about Josh. I mean, you are a prolific traveler. I mean, right now you're in Western Australia. You are living in Toronto. Hopefully your fridge is off and we're out of it before you left. I understand you sort of you grew up in Southeast Asia. Is that right? Do you have any
I grew up
interesting travel stories?
So I didn't do that much trouble when I was in Southeast Asia itself. So I grew up in Singapore. It was more so when I came to Western Australia. I think it's almost a bit cultural here. So Western Australia is, we're a really, really large state. We have 2 million people. And most of that, so maybe 90% or 95% of that is in our capital city. And our capital city is super isolated. It's a 5-hour flight to fly to the eastern side of Australia, which is the big cities such as Sydney, Melbourne, Brisbane. And because it's so isolated, it really grew this urge to travel. I think not just in me, but all my friends. It's just become super exciting to be able to travel and see the world, because we're so used to being from such an isolated place. And I think when I went to Toronto, if I was looking at the globe at the time, and between Perth and Toronto, it's almost exactly opposite sides of the globe.
Oh wow, really? That's crazy. Any favorite travel memories of yours that you want to share?
Something I really loved was, and this was always a dream of mine, when I was doing my PhD, I took 3 months off in the middle of the Northern Hemisphere winter, so January, to take the Trans-Siberian or the Trans-Mongolian. So I went from Beijing or through Mongolia and then through Siberia to Moscow over the course of 2 weeks.
Wow, that's crazy. That's been beautiful.
It was, yeah. Another thing about being from Western Australia is I'm not used to seeing snow in the least. So I saw the most snow I'd ever seen in my life up to that point.
I can imagine. How cold was it?
Funnily enough, thinking back to it, it wasn't as cold as when I moved to Toronto.
Oh, not a good sale for anybody coming to Toronto. Yeah, it does get cold here. That's true. Cool. Where do you want to go next? What's on your list of travel destinations?
So number one at the moment is to get back to Toronto and double check my fridge. I think, as you alluded to earlier, for those who don't know, I came down to Western Australia for a 3-week holiday, right when travel restrictions came in, and my fridge was still fully stocked, and I'm very nervous about that. Sometimes I wake up in the middle of the night worried about what's happening inside my fridge back in my apartment.
We'll get a hazmat team out soon to go check it out.
That's my fear.
We'll let you know. Well, it's been great for chatting with you, Josh. Thank you so much for joining us. Now you can go to bed. I think everyone in the chat really, or in the Twitch, really enjoyed it as well.